In this question, I'm asking you to explain mechanistically how you're turning this alcohol using aqueous acid into this alcohol. We kind of want to notice the difference between these two things. There's a 4-membered ring here. There's a 5-membered ring here. That should kind of get you thinking there's going to be a ring expansion at some point, which also should get you thinking there's probably going to be some carbocation formation in this. All right, so the thing to remember about alcohols, and I probably said this a million times, the thing to remember about mechanisms, and I probably said this a million times, is whenever you're given a mechanism question, don't look at the product and say to yourself, well, wouldn't that not form, or isn't that a minor product? Don't worry about major or minor or anything like that. When you're given a mechanism question, your only goal is to explain how these reagents turned into this specific product. So we want to make sure we're always working towards that product. All right, so I'm going to redraw the starting material here. Sorry, it's not as pretty. I didn't take my time on this. And I'm going to put the lone pair electrons on oxygen. Because remember, whenever you do a mechanism, it's always negative to positive. It's always the flow of electrons. Electrons to positive, electrons to positive. All right, I'm going to draw in the acid here. So aqueous acid, that's something like sulfuric acid dissolved in water, some acid dissolved in water. All right, so the first step here is our lone pair electrons on oxygen, they can grab that acidic proton, leaving these two bonding electrons behind on the oxygen to form just water. I'm going to draw that intermediate that forms there, which is basically just a protonated alcohol, also known as an alkyl oxonium ion. And now we have a good leaving group in the form of water. So when you protonated the hydroxyl group, you form a good leaving group, which is water. That oxygen can grab those two electrons that are bonding between the carbon and the oxygen, meaning that that water leaving group will leave. So now we have a tertiary carbocation, which is another reason why that water could leave, because the tertiary carbocation is stable enough to form. Right. So the next step is got to keep moving towards this specific product. So now that we have a carbocation here, a lot of things can happen, but we got to move towards this product. So this is a good time to have this ring expand open. So what I'm going to do here is I'm going to number all of the atoms of the ring involved here. So 1, 2, 3, 4, and then I'm going to make that carbon 5. This numbering has nothing to do with nomenclature. I'm just doing it so we can keep track of what's going on with the bonds here. All right, so when we look at this carbocation, something can happen here to expand this ring in the form of an alkyl shift. What I mean is these electrons between atoms 3 and 4, they could shift over and bond to atom 5, meaning 3 would be bonded to 5. 4 would lose the electron density and end up with positive charge. Or the electrons between 1 and 4 can shift over. It doesn't really matter, it form the same thing in this case. So what I'm going to do is I'm going to show the electrons between 1 and 4 shifting over to 5. What that means is atom 1 is going to be bonded to atom 5. So we're going to form a 5-membered ring here. We're going to form a 5-membered ring, and let's number this again. So 1, 2, 3, 4, 5. So those are our 5 atoms involved in the ring now. Now, on atom 5, if we look over here, atom 5 still has 2 methyl groups on it. So I want to make sure that I put those 2 methyl groups back on atom 5. When those electrons shifted between 1 and 4, when they shifted over to 5, 1 is now bonded to 5, which means atom 4 lost electron density, which means that's where the positive charge now exists. So we went from a tertiary carbocation to a secondary carbocation, which is destabilizing. But we also stabilized it by turning a 4-membered ring into a more stable 5-membered ring. All right, so we're still not at our product yet. We have to think about what's going on here. Well, you can see in the product, the 2 methyl groups are not on the same carbon, right? And we do form a tertiary alcohol. So the water can't come in and add now because that would not be the product where it's being asked for. But what can happen now is more electrons can shift. So either the electrons here of this methyl group and bonded to this carbon can shift over, taking that methyl group over there, or this one can. It's the same thing no matter which one does it. I'm going to show these electrons shifting over, and they're taking that methyl group along for the ride. So now I have the two methyl groups on different carbons. The carbon that I labeled 5, it no longer has those electrons, so now it has the positive charge. And then a molecule of water can come in and add to that carbocation. That's going to get our oxygen on there. So now, again, we have another protonated alcohol, an alkyl oxonium ion. So in this structure here, we just need to remove one of these protons now. And anything in here with lone pair electrons can do that. It could be a molecule of water. It could be the original alcohol we started with. It could be the conjugate base of the acid that we're using. Something in here is going to remove that proton, leaving these electrons behind to neutralize that, forming the final product that is being asked for here. And that's a good logical mechanism for how this alcohol, when treated with this acid, can turn into this alcohol here.